So maybe more so than we've learned with a metabolic pathway like glycolysis, the citric acid cycle is really a pathway that we have a lot of things that are feeding into or coming out of this metabolic pathway. Okay, and terminology that we use to describe that is we say that reactions are either anapleurotic, if they're things that add to or go into a pathway, or catapleurotic, if they're things that kind of we siphon off of a pathway. So just understanding those terms, okay? Something that's anapleurotic, you can think of ana being like add. So this is something that's going to add to a pathway. And catapleurotic, you can think of it being like cannibalize a pathway. So again, adding to a pathway is really in, so putting something into a pathway. Catapleurotic is cannibalizing. So cannibalizing a pathway, and that's really out. Okay, so right now we're going to talk about two catapleurotic sort of systems that we see with enzymes that are related to the citric acid cycle. So we're going to highlight them here, and they both have to do with a starting point of pyruvate. Both things that we've talked about already. We're either studied them already in detail, or we're going to study them in more detail coming up. But I want to highlight what each one of those are here. So over on the left side, I'm going to highlight some chemistry that happens with pyruvate here, and I'm going to circle sort of the pieces that are relevant to what we're going to see happening here. So that's this green part that we have here. So we're going to talk about some chemistry that can happen here with pyruvate. We're going to label the enzymes that we already know with what can happen here. So let's kind of zoom in and talk about what happens here first. So with what we have sort of in this green part here, okay, we're going to have pyruvate being having CO2 added to it. So the enzyme for that is pyruvate carboxylase. Okay, that's going to generate oxaloacetate. Remember, we talked about that being the first step in gluconeogenesis because we have to reverse that last step and get to phosphenylpyruvate. So the first step is pyruvate carboxylase, adding CO2 to pyruvate to generate oxaloacetate. And then we've got chemistry converting oxaloacetate to malate with malate dehydrogenase chemistry. And ultimately, once we get to malate, then we can export malate out into the cytosol, reverse all of those steps of glycolysis to essentially get to glucose. So putting that kind of in words over here, mapping on, again, enzyme chemistries that we've learned about, pyruvate going to oxaloacetate. And remember, pyruvate carboxylase only exists in the mitochondrion. So this is going to be mitochondrial oxaloacetate. So pyruvate carboxylase chemistry is going to handle that. And then we're going to have malate dehydrogenase is going to sort of handle the conversion to malate. And again, we're doing this in the mitochondrion here. So highlighting that pyruvate carboxylase is always only mitochondrial. This is going to be a mitochondrial version of malate dehydrogenase that can make malate that's in the mitochondrion. And then we can have chemistry to, or I shouldn't say chemistry, it's really that malate shuttle that's going to get malate out into the cytosol. And once we're out in the cytosol, okay, then we're going to be able to make glucose. And again, this is all in the cytosol. And that process is gluconeogenesis. So that's the chemistry that's sort of happening with this green part that we have over here. So now I'm going to highlight another option for pyruvate here. My fingers don't want to work on my iPad right now. All right, so highlighting a different option for pyruvate. So now pyruvate is going to be coming here, and we're going to be going through this part of the pathway here. Okay, so highlighting another option for pyruvate here. So I'm going to write pyruvate here, and then we'll kind of go through the steps that we're talking about. So another option for pyruvate, okay, is we are going to, and this is going to happen when we've got excess pyruvate. Let me change colors here so we can kind of see different enzymes here. So this is when we've got excess pyruvate, okay, because remember, gluconeogenesis is a need state pathway, so kind of operating differently here. So when we've got excess pyruvate, then we're going to have pyruvate dehydrogenase chemistry, making it into acetyl-CoA. So again, that's going to be a signal we've got excess acetyl-CoA. The enzyme citrate synthase is going to be responsible for combining acetyl-CoA with oxaloacetate. Okay, and then once we've generated citrate, we can export citrate to the cytosol. And we haven't gotten into the details of this yet. This is a metabolic pathway we haven't yet studied, but export of citrate to the cytosol is necessary for fatty acid synthesis. And again, that's going to be important for how we handle pyruvate when we are in a fed state, an excess state. So it's kind of like summarize that again with some a flow chart, if you will, here. So again, pyruvate here, highlighting this is when it's in excess. We're going to have pyruvate dehydrogenase chemistry. Okay, this again is going to be happening in the mitochondrion. We're going to be generating acetyl-CoA. Anytime we have excess acetyl-CoA, so this could be from excess glucose, but it could be from excess any fuel, acetyl-CoA is going to be converted into citrate by combining with oxaloacetate and using the mitochondrial enzyme citrate synthase. And now we can have citrate that can be exported. Okay, so we do have the ability to export. No.
I don't have an answer for that. Is there something else
I don't know what I said. We're going to export citrate to the cytosol. Okay, and now once we have citrate in the cytosol, this can be made into fatty acids, and that is going to be fatty acid synthesis. And so fatty acid synthesis ultimately can be made into triglycerides, and then all of that excess energy can be stored in adipocytes. Okay, so those are kind of two catapleurotic examples, but just to sort of highlight what sort of differentiates them is, let's see, let's choose a different color here. Let's choose purple here. This really is a need state, sort of catapleurotic system here using citric acid cycle enzymes. And then we have a fed state over here. So it's not to presume that, you know, catapleurotic, when we're cannibalizing a pathway, always happens in a fed state or always happens in a need state. Here are two examples of how they sort of operate differentially. Those are the two big things I wanted to highlight here, but I do want to point out and highlight a couple of other things that we're going to talk about. Remember when we talked about the metabolism of amino acids? Amino acids basically start by, our metabolism starts by saying, you know what, we got to get rid of this problematic element. So we've got nitrogen that we need to get rid of. So first thing that we do when we metabolize amino acids is we do deamination chemistry, and that nitrogen atom is going to be handled through the urea cycle. And then we're left with an alpha keto acid skeleton, right? Those are the two parts to an amino acid, the amino group and then the alpha keto acid skeleton group. Now, oftentimes what happens is that alpha keto acid skeleton group is going to resemble a metabolite from another metabolic pathway. Very often things that are citric acid cycle intermediates. Now, depending on what kind of citric acid cycle intermediate you have can help determine whether you are a glucogenic or a ketogenic amino acid. Remember that ketogenic amino acids cannot be made into glucose, but glucose can be made from glucogenic amino acids. So we're going to see a lot of this sort of system again when we talk about the metabolism of amino acids, but two that are just highlighted here that I want to point out. So again, we're seeing that there's going to be lots of amino acids that might feed in or out at alpha ketoglutarate, but specifically looking at these two sort of groups of ones, we are going to be talking about phenylalanine. So here's why phenylalanine is important. There is a metabolic disorder called PKU, phenylketonuria, and that means those are individuals who are unable to metabolize the amino acid phenylalanine. Now, normally not overly problematic with a natural diet, but aspartame, NutraSweet, that is an artificial sweetener that's made from two amino acids hooked together, aspartic acid and phenylalanine, and then it's got a little other modification to it. Tastes sweet on your tongue, but the problem is that any individual who has PKU cannot consume a lot of products containing this artificial sweetener because they have a hard time metabolizing phenylalanine. Okay, so that's that story. We're going to get to that story towards the end of the semester here. We're also going to talk about methionine, okay? So methionine is one of those really important amino acids. It's one of the sulfur-containing amino acids, okay? So we're going to talk about sort of the metabolic sort of systems that methionine metabolism is part of. And again, we're going to get to that when we do our amino acid metabolism, okay? So just introduction to a couple of other things that we're going to see, and highlighting and reviewing some things that we already have seen, whether it's need state use of pyruvate in gluconeogenesis or fed state use of pyruvate if we are in a sort of a glucose fed state.